Okay, so hello everyone. So today we're talking about the unit 2 of organic chemistry, which is resonance and acid-base chemistry. So first, let's define resonance in organic chemistry. So a resonance is a phenomenon in which electrons in a molecule can move or delocalize. So we're talking about the same molecule in which the electrons can move or delocalize across multiple atoms or bonds, leading to stabilization of the molecule. Okay, so let's look at some of the examples right here. So second question says, draw the resonance structures for the following molecules and indicate the major resonance contributor. Okay, so the first one we have the nitrate ion, right? So when we talk about the nitrate, we know that the nitrogen has 5 bonds, right? So it can form a bond with the oxygen, form the oxygen, one with the oxygen, and there's 2 left, right? Now, so we know it's a negative. That means that there's going to be a bond right over here, there's going to be a bond right over here, and then one of them is going to be a negative, right? Now, this is the charge, right? However, the over here we can draw a hybrid. Like I can say also that the resonance structure of this is this. Okay, and that's going to be the negative. I can also say that this is the resonance structure. All right. However, we can also draw a hybrid. Hybrid is all of them together, so I can draw like a line and then a dotted line right like this, a line and dotted line to an O, and then a line and dotted line to another O. So this over here can form the hybrid. Now, I know there's one charge that is distributed over 3 oxygens, so each of them is going to have one -3, one -3, and then one -3. So negative, they're distributed throughout. So if we can say this first one indicate the major resonance contributor, we're going to say it is the oxygen. Why the oxygen is the major contributor? Because it is where the charges and electrons are moving. All right, so this is the first example. And the second one's not so bad. The second one's kind of tricky. It's the same thing, so there's no resonance structure in the second one because there's not a shifting of electrons that's going on. So if we look at the second one, okay, we can just draw it as 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4, 5. Or we can do that again. So 1, 2, 3, 4. Okay, so we can have that and the hydrogens all over. And we can also do the last one, okay? So the carbonate ion. Carbonate's the same as the nitrate ion, so we can see the carbon. All right, so we can draw a hybrid. I'm going to draw it right over here, let's say. So I'm going to draw the hybrid of it. So there's going to be one dashed, one line, another dash, one line, other dash representing the hybrid. We have two, -2, that is distributed over 3 oxygens. So it's going to be this, -2/3 and -2/3. All right, and that's going to form the overall charge of -1. Okay, all right, so hope this is straightforward. It's just the resonance. Okay, next. So fill in the blanks to complete the following sentences. All right, so resonance structures differ only in the what of electrons. Okay, so you can take a second to look at this right over here. So the most important thing that we have here is the distribution, right? So distribution of electrons. So we have a different distribution of electrons, as you can see from the first example here, to the second one, to the third one, to the fourth one. This is the right answer because this is a hybrid of all of them combined. All right. B says resonance stabilization leads to a what in the overall energy of the molecule? Well, it lowers the energy. Why does it lowers the energy? Well, if you see it in this example that we had the carbonate ion, we had a -2 charge right over here in the molecule. However, we distributed that charge, right? We distributed that charge into -2/3, -2/3, -2/3. So what did that do? That lowered the energy of the overall molecule, all right? So we can shift in the energy. Sometimes you can choose one form of resonance structure to have a zero charge in some of the molecules. Other times, other resonance structures can form multiple charges, right? So, and that's something that we can discuss further when we talk about formal charges and how it is best to choose the resonance structure that leads to less of charges. Okay, so here we don't have that much in here in this example. However, we can see further examples of when you add resonance, you might add charges to the individual atoms of the molecule, leading to shifting the charges, but it's always better to lower the charge. Next, we can say that resonance can affect the what and the what of the molecule. Well, it can affect two things that are very important. The first thing is the stability. Okay, so the first thing that it can affect is the stability. The second thing is the reactivity. Okay, so it can affect the stability and the reactivity of the molecule. Perfect. Next, we move on to part two, which is acid and base chemistry. So this is also a very, very important topic. So first says define acid and base according to the Arrhenius theory. So the Arrhenius theory says that acid is a substance that releases hydrogen ions, which is H plus, in an aqueous solution. Right? So they release an H plus atom. Okay. The base is a substance that releases hydroxide ions in an aqueous solution. Right? So we can see that, for example, water can place in both of these. Right? It can sometimes act as a base, sometimes can act as an acid, because H2O is actually HOH. So in the first case, it is acting as an acid when it reacts with a base. Let's say that it reacts with NH3. So when it reacts with NH3, it's going to release its H, leaving an OH minus. All right. If we say it acts as a base, let's say, and it reacts with something like an acid, like an HCl, for example, it would give off the hydroxide, leaving an H plus. Or sometimes this H plus is written as H3O plus. Okay, these two are the same thing. Okay, next we can say define acid base according to the Bronsted-Lary theory. So this Bronsted-Lary theory is the one that's mostly used. So an acid substance that donates a proton to another substance, that's the most important thing here, is donates a proton. Okay, a base is the one that accepts a proton. Okay, so the first one we can say that the acid is the one that releases. Okay, and here's two, and then the base is the release. So here we have in the Arrhenius method, in the Arrhenius theory, we have both release, but when we say the Bronsted-Lary, we have the donates and accepts. So this a shift in the language right over here. Okay. Next we can have fill in the blanks to complete the following sentences. So in a Bronsted-Lary theory, the acid-base reaction involves the transfer of a what from an acid to the base. Okay, so we can see right over here. So we said and it's just right here, right? So we have involves the transfer of a proton. So a proton, which is an H plus. Okay, so I have a H plus that is transferred from the acid to the base. Why? Because the acid donates the proton to the base, which accepts proton. Okay, there's always also the Lewis theory of acid and bases, which says that bases have an excess of electrons, in which they donate electrons, and acids accepts electrons. Here we say we're talking about protons, we talk about Bronsted-Lary. Okay. Next, we can say a substance that can act as both an acid and base is also called the antiproduct. The product. An example is water, H2O. Okay, so as we saw right over here, sometimes can act as an acid, sometimes it can act as a base. Okay, next we say classify the following substances as an acid or base. Okay, so the first one is HCl. HCl is a very, very, very strong acid. Alright, so we can say, oh, that's an acid. How do we know it's an acid? Well, we can talk then about conjugate acids and bases. So if the acid has a very weak conjugate base. In this case, the conjugate base is going to be Cl minus, then this is going to be a strong acid. If it has a strong conjugate base, then the acid is very weak. Okay, next we have an NH3. NH3 is a base. Okay, how do I know it's a base? Because NH4 plus, when it has an extra proton, which is NH4 plus, that's an acid. When it loses its electron, its proton, according to the Bronsted-Lary, it's going to become NH3. NH3 is a base because it is the conjugate base of a acid, right? Now we have H2SO4. H2SO4 is an acid, okay? It's an acid. Why it's an acid? Well, that's an oxyacid because we have an oxygen in the atom, in the molecule. Okay, so we have an oxygen. But what makes a stronger oxyacid is then when you subtract the number of oxygens from the number of hydrogens. If it's more than 2, then this is a strong acid. Okay, if it's like less than 2, then it's a weaker acid. So here that's a strong acid, but here it doesn't say if we say weak or strong. Okay, next it says identify the conjugate acid-base pairs in the following reaction. Okay, so we know the acid becomes the base or the base becomes the acid. So in the first example, we can say, okay, so these two are conjugate acid-base pairs and these two are conjugate acid-base pairs. Okay, one of them gets a proton, one of them donates a proton. Okay, perfect. Next, we can say these two also are conjugate acid-base pairs, and these two are conjugate acid-base pairs. In the first one, the H2O played as a base, and it's accepted a proton, so it becomes an H3 plus, and an H3 plus. For the B, it's acted as an acid, so the H becomes an OH minus. Next here, we can say that, oh, these two are conjugate acid-base pairs, and these two are conjugate acid-base pairs. Okay? So, here are some of the questions that you can do. Pause the video, and then continue on to see what the answers are. Okay, so I hope you had a second to do these videos, the questions. So let's say, so resonance structure differs only in the what? So we answered this before, in the distribution, of electrons. Next, in a Bronsted-Lary theory, an acid-base reaction involves the transfer of a what? From an acid to base, we said it's a proton. Okay, next, a substance that can act as both an acid and a base is a product. Okay, and the major resonance contributor in the structure with the most what? Charge, separation, and octet violation. Now that's a new one that we didn't talk about. Okay, the major resonance contributor to the structure with the most minimized charge, separation, and satisfied octet violation. Sorry about that. Just gonna take this because we need a separation and an octet, right? So we need an octet. So that's gonna be a satisfied octet. Okay, so we have the one that has the minimum charge has the best satisfaction of the octet. So the lower the charge, the better it is to achieve the octet. Okay, so I hope this was helpful. Please leave us comments and if you have any questions. Okay, have a good one.